Hi. So in this video, we're going to be understanding pendulum motion. We'll first start off with simple harmonic motion, and the first part is going to be understanding pendulum movement. Okay. So this is this is the unit for waves. Okay. So this is the first unit that you're going to be seeing in waves. Now, in this case, we can just draw a simple diagram in order to explain pendulum movement. So let's say if I have a ceiling, and from the ceiling I'm going to attach a string of length L, and this is going to be our pendulum. Okay. Actually, let's draw it like this. So this is length L, and this is our pendulum. Okay. Now we're going to draw different positions for this pendulum as it swings from left to right. Okay. So in this case, this is what we're going to be having. Okay. So all of these strings have a length L, and the pendulum is going from the left to right and back. Okay. So this classifies as an oscillation, right? So oscillation is simply back and forth movement. Okay. So you're going to be seeing this as back and forth movement in a pendulum, right? And based on this, we can get simple harmonic motion, which we'll be seeing. Okay. Now, for any oscillation, we have to define some basic characteristics. So first of all, if you look at a simple harmonic oscillation or simple harmonic motion, this is a periodic oscillation, right? This is periodic. So what this means is that this oscillation keeps repeating itself, right? So if this is my pendulum bob, then this pendulum bob will continuously go from left to right, and it will keep repeating itself, provided that there is no friction, right? So if there's no friction or no force acting on the system, it can go on like this forever, right? So this is a periodic motion. It keeps on repeating itself, okay? Now, for each of this, what we can see is that we can calculate a period. So period is simply a time taken for the pendulum to make one transition and come back to its equilibrium position. So for example, this is one transition for the pendulum, right? So the pendulum starts off at its equilibrium position. It goes to the left, to the maximum direction in the left. It goes back to the right, the maximum direction in the right, and then it goes back to its starting position. Okay. Similarly, let's say if the pendulum starts over here and the pendulum goes all the way to the right, then it goes back to the left. It goes to its original position. Over here, the pendulum starts at the right, it goes all the way to the left, comes back to the right. Okay. So the time taken for a pendulum to start like this and then return back to its equilibrium position or its starting position, that's the period. Okay. So let's say if the time taken for a pendulum to make this journey, let's say that if this total time is 10 seconds, right, then the period t is 10 seconds. This is a period. Okay. That's what a period would mean, right? Now, the other thing that we need to learn about is the amplitude. Okay, so basically, yeah, so period over here is the time taken for one oscillation, for one complete oscillation. Okay, and then the other thing we need to learn about is amplitude. So amplitude is simply a maximum displacement from mean position. So maximum displacement from mean position. Okay. So what this means is that for every pendulum motion, we'll consider this to be the equilibrium. Okay. That's when the pendulum is going to be still. So in the sense it still is that, imagine if the pendulum is not moving, we would have that position, right? So the amplitude is simply the maximum displacement from the mean position. So let's say that if this is x1, this is x0, then the amplitude is just this distance, this maximum displacement from the mean position. Okay, that's what the amplitude is going to be, right? Okay, so I can erase this. So yeah, we looked at period, we looked at amplitude, right? And now we can move on. Okay, now basically, if you have this diagram over here, you can draw this angle theta. Okay, so we're going to be looking at this angle theta when we're going to be analyzing this. And let's say that the angle theta is the same, so you have a certain sense of symmetry over here. Okay, so therefore at this point the angle is going to be positive theta. Okay, at this point the angle is going to be negative theta, right? Okay, and at this point theta is going to be 0 because you just have this straight line. Okay, so we looked at the angles over here, and after this we can just start off by starting to analyze this. Okay, so the first thing you need to note is that normally what we were doing is that if we would be analyzing any sort of motion, we would always be using the straight axes, right? So this would be your straight uniform axes over here. But in the case of pendulum motion, we're going to be using a tilted axis. Okay, so if we take this over here, actually, yeah, so if we take this axis over here, right, we're going to be tilting this axis based on the direction of the pendulum. So over here the axis is going to be like this, then like this, and then it's going to go like this. So it's going to just keep shifting its position. Okay, so it's going to go like this, then up, then down. So as you can see, the axis is going to be shifting with the pendulum bob. Okay, so it's going to be shifting with the pendulum bob. So that's why normally we would be using a straight axis when we were analyzing motion, but in this case we're going to be tilting it. Okay, so this is going to be your tilted axis. So if you see, in this case we are over here, so you would have positive y, positive x, negative y. Okay, right, and this is actually similar to inclined planes. So if you remember in inclined planes also, what we did was that if this was an angle theta and if this was a mass m, then we tilted the axes to analyze the motion. Okay, we tilted the axes, and we'll be doing the same thing over here. Okay, so now we can look at the forces that are acting on the pendulum. So if you look at this pendulum, if you look at the forces acting on the pendulum, you've got this mass m. So you've got this gravitational force that's going directly downwards. So I'm going to make this for every pendulum position. This is your gravitational force. Okay, it's going to be acting directly downwards. And then similarly you have a tension force. Okay, so in this case you're going to be having a tension force that's acting upwards. So the reason the tension force would exist is because you can think of this example. Let's say if you have a string over here and someone is trying to pull it apart with both of their hands, right? If they start to pull the string apart, the string wants to go back to its equilibrium position. So if you're going to be applying applied forces to the right and to the left like this, then the tension would want the string to go back to its original position, so the tension will act towards the center. Okay, so over here the pendulum bobs, when they move, they want to stretch the string, but the string wants to go back, so that's why the tension is going upwards like this. Okay, so let me also draw the tension force for each of these diagrams. Okay, so this is going to be a tension force like this, and then this one also you're going to be getting this tension force. Okay, So we have listed everything that we need to know, right? And now what we can do is that we can analyze this motion, right? So if we draw this line backwards, we'll see that this angle is also theta by symmetry. And if we do the same thing over here, this will also be theta. Okay? Right? Okay. So if we draw it like this, then this is theta. And if you see, if I can make a right angle triangle. So this is exactly how we did in inclined planes. We made this right triangle. Okay? Right? So once again, we've got a tilted axis. The axis changes with the pendulum position. So you've got positive x, positive y, negative y. And similarly, you have the same thing over here. So this is y, x, negative x. Okay? That's what we have got so far. Now, in this case, what we can see is that we can take if you draw the axes over here, then we can decompose the gravitational force, right? Because if you see in the axes that we can see over here, right? This is x, y, and negative y. What you would be observing is that the tension force is acting in the y direction. So because the tension force is acting in the same place as the y direction, we don't need to decompose it. We don't need to find the components of this force. We only need to do it for the gravitational force because the gravitational force is not acting along the direction of the axis. Okay? So that's why we'll find the components of the gravitational force. Okay? So just think of it this way. You've got a gravitational force that's acting downwards. You know that this angle over here is theta, as we can see, the symmetry of it. So if this force is Fg and we know that this is 90 degrees, then we can just find this angle. So we can say that this is Fgx, or the force of gravity in the x direction. This will be negative because you're going in the negative x direction. Okay? And this is going to be negative Fgy. The reason it's negative is because the gravity is acting in the negative y direction. Okay? So if you find this, you can say that sine of theta is negative Fgx by Fg. And similarly, you can say that cosine of theta is negative Fgy by Fg. Okay? So if you look at this over here, you can just say that in this case, Fg sine of theta is negative Fgx. Therefore, the force of gravity in the x direction is negative Fg sine theta. Okay? Now, the other thing is that we don't really care too much about this Fgy force. So the reason we don't care about the force of gravity in the y direction is because Fgy acts over here and then the tension force acts upwards. So both of these just cancel each other out. Okay? So because they're going to cancel each other out, we're not going to be looking too much at them. Okay? So that's why our main focus is the force of gravity in the x direction, or the x movement. Okay? So actually what we see over here is that the sum of forces F net in the y direction is 0. It's 0 newtons. So in this case, if I draw a pendulum bob over here, right, as you can see, the pendulum is only going in the x direction. If you remember, the axis is shifting. So the axis is shifting, so you're going in this you're going in this direction. Okay? But the pendulum is not going up and down, so it's not going in the positive or negative y direction. It's not going up and down. It's not going up and down in the y direction. It's only going in this x direction. So this x-axis, as you can see, going through the x-axis. This is the x-axis going through this x-axis. It's only the x displacement. Okay? The y displacement does not matter because the tension force, because this tension force and this gravitational force, they cancel each other out. So we don't care about that motion because F net in the y direction is 0. Okay? So F net y becomes 0. So what we can say is that therefore the net force is just going to be coming from your net force in the x direction. Okay? And this net force in the x direction, by using Newton's second law, we can say that this is mass times acceleration in the x direction. Okay? Now, if we see carefully, the only force that's going to be acting in this x direction is going to be this FGX, right? It's going to be this FGX force. Okay? Right? So therefore, what we can say is that the net force in the x direction is mass times acceleration in the x direction, which becomes negative FGX, as we have seen, and this is minus FG sine of theta. Okay? As we can see over here. So therefore, we see over here that mass times acceleration in the x direction is negative FG sine of theta. Mass times acceleration in the x direction is negative mg sine of theta. So you see over here that acceleration in the x direction is negative g sine theta. Okay? Now, this is a pretty important result because based on this, we can make some conclusions or some intuitions about your simple harmonic motion. Okay? This is where we can apply some of the intuition over here. So what we can see in the simple harmonic motion, first of all, is that the acceleration in the x direction is proportional to the negative x, or the displacement in the x direction. Okay? So it's where this negative sign comes from. So the reason is because if you have a pendulum bob over here, right, this is a pendulum bob, as you go maximum towards the right, as the displacement in the right is, extremely high, as you see over here, okay, then in this case, as the x goes to the maximum, the net force acts to the left. So even though you're in your positive x position, which is over here, this is your maximum displacement in the positive x position, the net force is acting in the negative y direction. Negative x direction. Okay? And then in this position, you're towards your maximum negative x position, right? This is the maximum you can go in the negative x direction. But then what you'll see is that the acceleration is going to act towards the right. Okay? So if your displacement is negative, the acceleration is in the positive x direction. If your displacement is positive, the acceleration is in the negative x direction. Okay? So for example, over here, this is your max x, right? But the acceleration is negative g sine of theta. So it's acting over here. But over here, this is your minimum x. But the acceleration over here is positive g sine theta. Okay? So the acceleration is proportional to negative x. Now, the reason why this happens is because, so this is simple. The acceleration in the x direction is negative g sine theta. So what we have defined is that if the angle goes in this way, it's the positive theta. And then if it goes this way, it's negative theta. So at your maximum x position, your acceleration in the x direction is just negative g sine theta, right? But then in your min x position, the acceleration in the x direction is negative g sine of negative theta. Okay? So this just becomes negative sine of theta. And then these two cancel out, so you get g sine theta, which is what we got over here. Okay? So that's one result we have seen, that the acceleration is proportional to negative x. Okay? So that's the first intuition we get about simple harmonic motion, that the acceleration in the x direction is proportional to negative x. So therefore, you can say that the force is acting towards the equilibrium position. So, no matter where the pendulum bob is going to be going, no matter where the pendulum bob's going, the force always wants it to go to the equilibrium position. So if you go too much to the right, the force wants you to go back to equilibrium. If you go too much to the left, the force wants you to go back to equilibrium. Okay? So therefore, the net force always acts in such a way that the pendulum goes to its equilibrium position over here. Okay? That's what simple harmonic motion is. You want the force acts in such a way that the spring or the rope or the string wants to go back to the equilibrium position. Okay? Now the other intuition you can see is that the acceleration in the x direction will be proportional to some value of theta. Okay? So actually the way you can think about it is that the absolute value or the magnitude, not the direction, not positive or negative sign, just the magnitude of this acceleration will be proportional to theta. Okay? So in this case, what you can see is that over here, once again, if you draw this pendulum bob, right? And this is theta and this is theta. What you'll see is that at this position where the acceleration in the x is negative g sine of theta, over here theta in the equilibrium position is 0. So therefore the acceleration in the x direction is negative g sine of 0, which is 0 meter per second squared. Okay? Right? But then suppose if you go all the way to the right, then theta is rising, correct? So what we can see is that if theta rises, then sine of theta will also rise. Okay? This will only happen until theta. This will only happen when theta goes from 0 to 90 degrees. Okay? So we can sort of just draw a sine curve over here. So then this is sine of theta, this is theta, and this is your sine curve. Okay? So this over here, sine of theta will be 1, and this angle is 90 degrees. Okay? So as you can see that as theta rises, sine of theta will also rise as you go to this 90 degree position. Okay? So essentially what we're seeing is that if theta is rising, then sine of theta rises, but the maximum it can go is 90 degrees. So that's why we draw this hard line over here. We say that at this point you've got 90 degrees, so theta cannot go any higher than that. Okay? So that's why this pendulum will only go, and that's why if you see this pendulum, the maximum displacement this pendulum can make is this way. Okay? This is the maximum it can go because theta is 90 degrees over here, and then that's how you get that maximum displacement. Now the pendulum always doesn't have to go to 90, but let's say if you make it go to 90 by applying a higher force, right? If that's the system that you design. Okay? So therefore we can say that over here the acceleration in the x direction is negative g sine of theta, and as theta rises, sine of theta rises, which goes from 0 to 90 degrees. And so therefore you can say that the magnitude of the acceleration also rises. Okay? As theta rises, the magnitude of the acceleration rises. Okay? So that's why we get this intuition that this acceleration in the x direction is also proportional to some form of theta. Okay? So these are the two intuitions that we have got from this pendulum motion, right? And later on, we'll be moving into mass spring systems. And so in mass spring systems, we'll get an equation that the acceleration in the x direction is negative omega squared x. And in this case, omega is just delta theta by delta t, right? This is your angular velocity. So therefore, as you can see, the acceleration is proportional to some value of theta, and this acceleration is also proportional to some value of negative x. Okay, so that's all. We looked at, in summary, we looked at pendulum motion, we analyzed the free body diagram, and the main intuition we got was that in simple harmonic motion, acceleration is proportional to negative x, and acceleration in the x direction is proportional to some form of theta. The main thing you need to remember is that in this case, if theta rises, sine theta rises. So this only happens from 0 to 90 degrees. As we can see, this is 90. This is the only time it can happen. And over here, the thing is that this pendulum cannot go any higher. It can't go this way, right? You want it to stay at 90. That's the maximum limit that we impose. Okay? All right.